Okay, so in this video, I will be explaining the general architecture of the embedded firmware for our microcontroller. So this is this board here, and I will explain how the firmware works and what are the main parts that you should know. So, for example, where the threads are created, where's the entry point of the program, and so on. I won't be going into too much detail about each sensor and about how everything works because each sensor will have its own dedicated video with how it was programmed. But we will go through some of the most basic parts of the project so that you can understand how uh, the architecture is. So for this video, I will assume that we've already followed the getting started video where I showed you how to clone the project and how to get the latest libraries and how to flash the firmware onto the board. So if you haven't followed this video yet, so I recommend you to watch this video and to follow the steps first. So let's get started. So here on the left panel, you can see all of the different projects and folders that are used in Orion. So as a reminder, this is only the low-level firmware, but we will have also another video dedicated to the higher level firmware that we've written on the Jetson. So this is the firmware. The firmware that you can see here is the one that runs on the microcontroller, and we have another one that runs on ROS, so ROS 2, which interfaces with the microcontroller also, and also is used to send data to all of the other subsystems like navigation subsystem and the robotic arm and so on. So here we will only focus on the microcontroller part. So on the left panel here, you will first see the external loader. So this is used to program the external flash memory, which holds our firmware. So I will have another video explaining in more details how we generated this file and how we wrote a custom bootloader to generate this file. We then have here a panel for the IMU calibration. So this one is separated into three parts. We first have the accelerometer calibration, the magnetometer calibration, and a way to plot the quaternions that we receive from the board. So I will have a dedicated video on how to calibrate the IMU hat. Okay, then we have the Orion boot. So this is a project which flashes the bootloader onto our board. So we've written a custom bootloader, which you can see here. And this custom bootloader configures the QuadSpy flash memory and sets it in a way so that we can add a program onto that flash, which can then be used in further in another part of the project. So here we have another project which is used to generate the external loader file. So you won't actually be using it, but just in case you really want to create your own bootloader, or if you want to have more control over what is happening in this project, I will still dedicate a video which will be explaining the boot and the external loader part of this project. Then here we have the Orion firmware, which is basically the main, uh, like the actual firmware that runs on the microcontroller and the one that we use for the competition. So I will focus this video on this part of the project. And you can also ignore the Orion test bench. So this is just a test project that I added for presenting the board as a semester project, because this board here was designed as part of a semester project, and I needed a quick way to test it, which is why there is also this Orion test bench project. So let's have a look at the Orion firmware project. So first, you can really ignore the binaries and includes. So the includes here just are a list of all of the folders that have .h files. So I actually just cleaned it a few weeks ago. So here we can see everything that is included in the project. Here in the core section, you will have the generated code from STM32 cube. So how does this project work actually? So here you will see the .ioc. So the .ioc, if you open it, so you can either migrate or continue. I will continue because I don't want to update the project. So if you open the IOC, you will actually see how the pins are configured for this project. Okay, so let's have a quick look. So here, this is a microcontroller, and you can see how I configured each and every pin. So all of the HAT are set as GPIO outputs. The LEDs are also set as output. We have here the debug pins for the external debugger, the I2C, and so on. We've also defined here all of the connectivity settings. So for the I2C, for example, we set it as fast mode. For the SPI, we set it as Motorola 8-bit MSB first, with a prescaler of 2 and 2 edges for the clock phase. So you can have more details about this part by looking through the datasheet and through the reference of the microcontroller. The UART here, UART1 is used is connected to the USB to UART of the microcontroller, which goes through this USB port here, and we operate the UART at 100 at 900 to 921,600 bits per second. So this is the baud rate that we use, and it also uses the DMA, the direct memory access, to offload the computation to the so that we don't overload the CPU. And yeah, so we have also the CAN bus that was configured with all of the timings according to the bit timings that we have calculated for our application. So there will also be a dedicated video on how we computed all of these cycle and width for all of the bit timings. So there will be a video dedicated to that. And yes, so there are also other settings that are very useful, like the timers. So we've configured the timers to generate PWM signals. So here you can see that they are not configured as PWM, but as you will see, or as you have already seen in the video explaining in detail the HAT that was connected to control the servo motor via PWM, you'll see that we actually configured the PWM in a way so that it can be dynamically configured. So more details in the servo and level shifter HAT video. So here are the timers. Here you can look at the system core. So we have the watchdog timer, which allows us to reset the board if it gets stuck. We have, of course, the DMA that is set for the UART, as I've said before. And we also enabled the CRC computation unit. So there will be more details about this in the communication protocol section, in the communication protocol video for the custom communication protocol that we use. And also here are all of the settings for FreeRTOS, which is the real-time OS that we use on this project. So this is a very important part of the system, and you should have some knowledge about how FreeRTOS works. So if I go through it very quickly, we can see that I use a tick rate of 1000. So this is the recommended tick rate. And the most important settings are here in the where is it? It is in the config parameters. And here we can see the total heap size. So this is the heap size that we use. It's fairly large. And yeah, you can have a look at all of these settings, but normally you shouldn't touch them because we've tuned them to work with the firmware that we are using. All right. So now let's continue with the rest of the project. So more details about the IOC and how to configure it will be explained in another video. So when you configure the IOC, just as I did, when you regenerate the code, so you can regenerate the code here, it will automatically generate code inside of these files. So for example, if I configure the SPI or the I2C pins, it will automatically generate all of these codes, and so that I don't need to write it myself. So you can see that all of the generated code is outside of what is called user code. And you can add your own code here inside of these user code comments so that when you regenerate the code, it won't be overwritten. So this is what you need to know for the core. So we have the source and the ink. So all of these are generated by STM32 Cube IDE. And the one thing that you have to know is the main.cpp. So this is the entry point of the program. And if you look at this, you will see how the program starts. So first, it will go inside of the int main function. It will first initialize the microprocessor and also the peripherals and the clock. It then generates all. It then initializes all of the interfaces. So this is all generated by STM32 Cube. Here I've added this to stop the watchdog when we are in the debug mode and when we are actually pausing the program so that the microcontroller does not reset when we are trying to debug it. Then we start the timer 5. So timer 5 is used to keep track of to have a very precise way to keep track of the time, because FreeRTOS, as you've seen in the settings before, runs at 1000 Hertz. And for the IMU hat, we use a MACDRIT filter to do the sensor fusion, which needs a way to measure time in a more precise manner. So this is why we use an external timer. We then initialize the kernel of FreeRTOS and initialize FreeRTOS, and finally start the kernel. So if you look through the MX FreeRTOS init, you will see here two functions which we have added. So we actually initialize the system and initialize the telemetry. And then afterwards, we also start the thread for the blinking of the LED, the green LED on the board. So this is this LED here. One of these two will be blinking in green. Okay. So what does these two functions do? So the system init function, if you go inside, this is a class, a system class, which is actually, so I will show you where it is. So you can go into the system here and inside of core, and then you have ink and source, and you will see the system and telemetry classes. So let's look at the system class. So the system class is basically a class that is full of static functions so that we can call it without creating an explicit object. And we will have here all of the functions that are related to the system. So for example, so let's go through each function individually so you have a proper understanding of this. So the prioritize 3.3 volts LDO will set the cell 3.3 volt pin to high. So if you don't remember what this is, if you look through the schematic and you look through the power connector here, there is this MOSFET here, and if you actually turn on this pin, it will turn on the MOSFET and it will set the PR1 here to the ground. And by setting this PR1 to the ground, we will prioritize the VIN2 here, which is coming from the LDO, right? So if you want to prioritize the LDO, we need to set this pin to high. And now if we want to prioritize the buck converter, so this is the power that comes from the Orion Power PCB, so from this PCB. the power that comes from this PCB and is connected through this connector is also connected to this part of the circuit, so to this net here, and we can select between the two by setting by calling this function. And then we have some functions here that tell us whether or not we are using the USB 5 volts or the LDO 3.3 volts. So this is the same thing. If we look through this section here, not this section, if we look through this section here, we see that we will have a status pin, and this pin will tell us whether or not we are using this or this. And the same can be said for the 5 volt status, whether we are using it from the external buck converter or from the 5 volts that is coming from the USB port. So these are some of these functions. Okay, now we also have the enable Mesa 5 volts output and disable the output. So this is related to these pins here. So this is the Mesa board, the power supply, and we have here the two control pins which control the MOSFETs for the power from these connectors. So I already I already said it in the video that was detailing this design, but this part right now is not functional. You will need to move this MOSFET on the lower side because we can't really control this power with high side switching. You need to do low side switching. So this part of the circuit is not functional right now. But I still added it in the code just in case. Okay, so we then have the enable yellow LEDs and green LEDs. So maybe not green, just yellow LEDs. So this is just a way to turn on this LED. We also have a way to blink the LEDs. So the yellow LED is used as a warning or as a status, just as a way to see if there are any problems in the program. So we have a custom function just for blinking the LED. So it's a very simple function that you can see here. Then we have the functions for turning on and off the LEDs of the CAN bus. So these are these LEDs here and here, which display the status of the CAN bus. And here we have the functions for enabling the silent mode of the CAN bus. So if you look through the PCB design here, you not this one. Oh yeah, this one actually, yeah. So if you look through the node-to-node connectors, you will see here that we can have the CAN1 silent and CAN2 silent to control the mode of that CAN transceiver. Okay. Then we have the update node ID function. So this function will read the pins that are set on the dip switch. So according to the state of that dip switch, it will read it and then compute the ID according to that dip switch and set the node ID, which is part of that class, to that value. The get node ID returns that node ID without updating it. And then we have some functions here that you will understand if you look through the communication protocol video. You will understand how this works. So we basically define a packet that was just for controlling a laser through the 5 volts output of Mesa. So if we then read the packet, and depending on the enable field of that packet, we enable or disable the 5 volts output. And we only do it if the board is using USB the 5 volts from the buck converter, right? So this is for the system, and I will also have a dedicated video for the shell that we are using. So let's first have a look at this init function. So first we create a shell, So the shell here is a custom terminal that we use for debugging purposes. So I will have a video for that. We then create a watchdog thread. So I will explain later where all of the threads are set. We disable all of the LEDs, disable the status LEDs, and we can then configure the LDO as well as the node ID and stuff. And we also create the probers and the threads for the FDCAN. So I will explain what these are later in this video. Okay, so let's look at the telemetry now. So if you remember, the function here called the setup of the telemetry. So if you look through the setup, you will see what this is. So this will create the different communication classes or objects that we need to communicate through our custom protocol. So there will be more details in the communication protocol video. And this one also has the function for handling the ping packets that are sent from the Jetson to this microcontroller, as well as a way to set the ID for the CAN bus and so on. So more details about this in the communication protocol video. All right. So this is for the telemetry part. And now, how does the threads work? So as you have seen in the system.cpp, we created a prober thread. So what is this? So this is a thread which are defined here in system thread. So if you go in the thread part, you will have here a list of the threads. So the threads, all of these are threads that are inheriting from the thread class. So let's have a look at the thread class. Okay. So the thread class here has multiple constructors depending on what type of control we want to have. And the thread has an init and a loop function. And we can also terminate it, have the status of that thread. We can set the frequency of the loop, as well as print data into the terminal. And yeah, so there are many things that we have written for this thread. So let's have a look at the definition. So first, we have the default stack size, which is how much memory we want to assign to that thread. So 2048 is a pretty good number, which worked for all of the threads that we are using. And now if you look at this, you will see that in the run part of that thread, we will first create the thread. Then we can wait for a few milliseconds. You then call the init function of that thread. So the init function will be defined by the user, so by you. And then while the thread is running, we will then call the loop function, which is also defined by the user, and wait for a certain number of time, which is defined by the get tick delay, which we can set when creating the thread. Okay. So then there are more functions here for printing. So I won't go into too much detail, but you can have a look. So it's a very simple, but well, not that simple, but you will have more details when I will talk about the custom shell, like what the console is here and how the printing works. Okay. So this is for the thread. So now let's talk a bit about the prober thread. So the prober here is the thread that is launched by the system at first. So these are the first threads that are launched along with the watchdog thread. And the goal of the prober thread here, so it is inheriting from the thread, as you can see. And the goal of that prober thread is to launch other threads. So if you look through the init function here, what we first do is scan all of the I2C buses. So it would be I2C. So we actually create a thread on I2C 1, 2, and 3. And each thread will have a look at every sensor that is connected to its I2C. So this is just a code to write in the terminal what type of sensor is connected on the port. Once it has gone through the init function, it will go through the loop function. Okay, so this is the code for the prober. And what it does basically is it checks for every sensor. It will check if it is connected. So it will probe the I2C. So what this does basically is it checks if there is a device with a certain address, which is given by this, for example, X48. And it will check for this address. It will do the same for every sensor that can be connected. Okay. And if it detects that sensor, so let's have a look at the IMU, for example. So this will check for the BMI 088 and the magnetometer. So this is the IMU and this is the magnetometer. And if they are both present on this I2C bus, it will then create the relevant thread. So in that sense, in that case, it would be the thread that computes the quaternion for computing the heading of the rover. It will also set the frequency of that thread. We also decide to blink the LED, so the yellow LED, a certain number of times. So in that case, it would be the number of time given by I2C num. So this means that if we plug this hat onto I2C1, it will blink once. If it's I2C2, it will blink two times, and so on. So if it's not clear, the hat 3 here is connected to I2C3, hat 1 is connected to I2C1, and hat 2 is connected to I2C2. So once it has created the thread, it will take the semaphore. So what this does is it will stop the execution of that thread at this point here until the semaphore is given. All right. So what does this mean? If we look through the thread, the AHRS thread here, so it's a quite complex thread that I will explain in the IMU video. So if we look through this, let's look through the HRS thread definition. So it's a fairly long function, but we can look through semaphore. Oh yeah, it's a bit hard to do that, but let's look through the loop. Okay, so we have the loop here, and you can see that whenever, if we have any error with the thread, what it will do is it will reset the prober here. And when it resets the prober, we will give the semaphore, which means that it will continue the execution of that prober. So basically, imagine that I am connecting, that I don't have anything connected to the board here on I2C1. So if there is nothing connected, just like here there is nothing connected, the prober here will run through every if function. Every one of these functions will return false because there is nothing connected, so we just run through. And once I connect, let's say the IMU, it will detect this sensor and this sensor, so these will return true. It will then launch this thread here and then take the semaphore. So this means that it will stop the execution at this line. And then the AHRS thread will be started. And if I unplug the sensor, it will give an error and it will call this part of the code, which will reset the prober. So it will call the reset prober, which will give the semaphore, and this will allow this prober to resume its execution from this line here. So it will go to this line, then this line, and it will repeat until another sensor is connected. Okay, so this is the principle of that prober. Okay, so that's the gist of the system. Now let's have a look at other parts of the system. So here we have Broco, which is the library that we use that we have written actually. And this is a cross-platform library which contains all of the functions and the classes for communicating between the boards and to Jetson. So it's a very, very modular library and a cross-platform library which is actually written to be used as a ROS package, but we can also use it here as a normal included folder in our embedded firmware development. So in our case, we use the Rokan driver.cpp, but I will give more details in the communication protocol video. Okay, so this is for the library. You just have to remember that Broco here is a submodule and is not a standard folder. So any modification to this will have to be pushed to its own repository on GitHub, and then we will need to update the reference to the commit on the main repository which contains the firmware. So more detail about this in the communication protocol video. Then we have the debugging here, which contains all of the functions that we have written for the custom shell and the custom terminal. So we have multiple functions here for interacting with our board via the serial port. So I will give more details about this also in the custom shell video. Okay, this for the debugging. The lang here contains custom operator functions that we use for so that we can use the new and delete functions to be compatible with FreeRTOS. So you don't really need to know this, but you should include this file in the project. And I've already talked about the threads. We have the utils function here, which I will explain why we need these in one of the sensor videos for the spectrophotometer, for example. All right, so that's it really for this part of the project. So now if I do a quick summary of how it is structured. So we have the core here, which contains the functions that are generated by STM32 cube. The main entry point of our program is the main.cpp. This function here configures everything, like all of the interfaces, and it starts in the init function here. It will start. It will call the MX FreeRTOS init function. This function will initialize our system and the telemetry, which is, so the system is for creating the threads and the telemetry for the communication. And in the init function of the system, it will create the probers and some other threads, while the telemetry here will set up all of the handles and everything that we need to communicate between the boards and from the board to the microcontroller, from the board to the Jetson, I mean. Okay. So that's it for this video, and I hope this gave you some more insight for this project. And if you have any question, of course, you can ask me on Slack and I will answer. So there can be some fairly technical questions, technical details that I haven't covered. For example, what this is, or what the watchdog thread is, and so on. But I might cover this later, or you can ask me if you have any questions. All right, so see you in the next video.